Hey guys, today we're going to take a look at vector and parametric equations in 2D. So first of all, the idea here is we are going to be given a point. We're going to start with a point. You can see I already messed this video up and had to restart, and we're going to have a vector. And this vector is going to be what we call our direction vector. This is going to tell us where we go. So the idea here is I'm going to start at the point 5, 3. So I'll start right there at that point. And then I'm going to follow the direction of m, which is negative 8, 2. So I'm just going to go back 8, which will take me to negative 3. And then I'm going to go up 2, which takes me to this point right here. So this vector right there gives us our direction. So now you know how vectors work. We can move that around and it's the same vector. But because I've given you this point to start with, what this does is this makes it so that this is our line right here. So that right there is the line that we've created. Okay? So if you were given 2 points, of course, you could, much like making slope, you could create the direction vector. So in this case, we've got A and B here. So I'm going to have 1/6 minus 4/3. And for my y, I'll have 3/2 minus negative 2. And so this here will create a direction vector for us, which will be negative 7/6 and 7/2. Okay? So let's take a look at what the actual equation is going to look like, and we're going to make it look more complicated than it really is, because that's how we usually do things. And so the idea here is I'm going to be giving you P naught and P. So these are the position vector or general point. Well, I'll show you. Hold on. So let me just write out the equation. So what the equation is going to look like is it's going to be, my stylus isn't working again. There we go. All right. Equal to R naught plus TU. All right. So what this is the vector R is, so this is the position vector of a generic point on the line. So this is the vector, is the vector that will point to any point that lies on our line, okay? So that's the position vector of a generic point on the line. Let me, okay, so then the next thing is going to be R naught. So this is a vector that's going to point to it's going to point to a specific point that we know is on the line. So this, so this is whatever. It's exactly what I just said. It's a vector that points out to where of a point that we know where it is. Okay. All right. So then the next thing we have is we have U. So U is our direction vector. In other words, it's a vector that is parallel to the line that we're dealing with. Okay? And then finally we have T. And T is just a real number that corresponds to the generic point P. So as we change T, we'll find a different point lying on our line. It's similar to the X when you're just writing out an equation the way you normally would. Okay? So that's all of the components. What's interesting about the vector equation, and very important, is that of course every line can have an infinite number of vector equations. So just because you have a vector equation and I have a different vector equation doesn't mean it's a different line. They can both actually represent the exact same line. So the vector of equation of a line is not unique. Okay, so now we can take this idea of a vector equation and we can break it down into what we call parametric equations for the line. So first of all, we have, we'll just break it down into component form, and that will just give us that'll show you where this comes from. So what we do is we say, instead of writing that R vector as R, hold on, let me zoom in, we're going to write it as XY, and it is a vector, of course, whoops. And so then what we're going to do is we're going to take that starting one, that starting point, that point that we know is on the line. We take its vector, and then we add t, and it's the same t we had before, times the x component of the position vector, or the direction vector, and the y coordinate of that vector. So there we go. So this is the exact same thing. You do still have to write t as an element of the real numbers. All right, and so there we go. And what we're going to do with that is we're going to split it up, and this is going to create our parametric equations. So we're going to split it up into two parts. We're going to have x, and you're just going to write like this thing. I'm not very good at drawing those. You're going to have x and y, and you're going to split it up into two equations. So you'll have x naught plus tux and y naught plus tuy. All right, and again, you do still have to write t as an element of the real numbers, and these are called our parametric equations. Okay? So we're going to jump ahead. That last page was all made up of questions that you are going to work through. We're going to jump ahead to parallel lines. So there's a couple things here. So if we have two lines, L1 and L2, and they have the direction vectors U1 and U2, we can determine that the lines are parallel by doing a couple different things. Some of these are obvious, but some of them are less obvious, and some of them are useful, and some of them are less useful. So the first thing is that, first of all, if we know that the direction vectors, U1 and U2, are parallel, if they're parallel, if the direction vectors are parallel, then the lines are parallel, which makes sense. Okay, but another way we could do this is we could say that U2, not the band, is equal to KU1. Sorry, I guess I should have started with there exists a K. There exists, which is an element of the real numbers. So there exists a K such that this is true. Okay? If there exists a K such that that is true, then we know that these are parallel lines. I mean, that means exactly the same thing. It just means they're going in the same direction. Okay? Now, another way you could say this that's sometimes useful is we could just say, well, if we take the x component of the second line and divide it by the x component of the first, or vector, I guess I should say, it will be equal to if I do the same thing with the y components, okay? And what's interesting is that that will also equal k, and it will be the same k as before. Now that's somewhat useful. Possibly the most useful thing here, and some of you may have already figured this out, is we can just take these two vectors and we do the cross product. And if it equals the zero vector, then we know that those two things are parallel. All right? So there we go. All right, so let's jump ahead to perpendicular lines here. This one's a little bit more straightforward. Okay, it's the same idea though. Okay, if we know that the direction vectors are perpendicular, then we know that the two lines are perpendicular. So what's the easiest way to do this? Well, we can use the dot product on this one. If we take the dot product and it equals 0, then we know we have perpendicular lines because that was just a characteristic. Okay, so an example of a couple vectors in 2D that are perpendicular to u, we'll call it v, and it would be negative b a. You can test these if you don't believe me that these will give you a dot product of 0, but they do. Okay, you can have b a, or sorry, it's negative a. Those are two examples of vectors that would be perpendicular. All right. All right, so finally, we're going to jump down to special lines. And this one kind of may seem obvious to some of you. If it does, good. That means you're smart and you know what you're doing. So if you have a line that's parallel to the x-axis, what it will be, that direction vector will have a 0 for a y component. Okay? Now, Granted, it has to have a direction vector that's not the 0 vector, because that's ridiculous. You can't have that. So we have to say that the exponent can't equal 0. And then, of course, if we wanted one that was perpendicular, or parallel rather, to the y-axis, same thing. All right? So that's fun. All right? And that's it. So until next time, go Sabres.